Welcome to the Deep Dive. Today we're diving into something we see every day, but maybe don't think too much about its inner life. Water.
That's right. It seems so simple, but it's got this incredible secret life.
Exactly. We want to explore those dramatic transformations it's always undergoing. From solid ice.
To soaring steam. And it's all driven by physics, really.
Pure physics. And to really get a handle on it, make it relatable, we're going to follow the story of just one H2O molecule. We can maybe call her Aqua.
Aqua, I like it. Following her experiences really helps visualize what's happening at that microscopic level.
Let's start right at the beginning, in what we're calling the frozen kingdom. Ice.
Okay, the solid state. So picture water as ice. Those perfectly formed, sometimes shimmering crystals, maybe with sharp geometric edges. They're locked into this beautiful repeating pattern. It's called a crystalline lattice. Think of it like a perfectly organized molecular structure.
Locked in. So Aqua's just stuck in one spot.
Pretty much. Her position is fixed relative to her neighbors. It creates this, very serene and still landscape down there, almost static.
So very limited movement then. How does that work?
Exactly. They aren't completely still. That's important. But their motion is reduced to just subtle vibrations, like a tiny, gentle shivering in place.
And that low movement is tied to the temperature.
Directly. It's because thermal energy has been removed. Less energy means less movement.
Okay. And what's actually holding them together so tightly in this rigid structure?
That's the key. Intermolecular forces. These are the attractions between the molecules. In ice, these forces are really, really strong.
Strong enough to lock them down.
You got it. That's what gives ice its solid, rigid structure. But things get more interesting when we add some heat.
Okay, let's move on. Inject some energy and head into the liquid lake.
The transition phase. Melting.
So what's happening now as that ice starts to melt? What are the molecules doing?
It's quite dramatic, actually. Heat particles, you can imagine them bombarding the frozen molecules, hitting them with energy. So Aqua and her neighbors, they stop just shivering gently. They start vibrating much more vigorously, really shaking quite violently in their spots.
Wow. And those strong forces we talked about in ice, what happens to them? Do they just snap?
They don't just vanish instantly. The intense shaking makes them weaken, stretch. They become more elastic, kind of strained.
Okay.
They start to break, but then they can reform again. It allows individual molecules or maybe small clusters to sort of wobble free for moments and slide past each other.
And that's what we see macroscopically as melting, right? The solid structure disappearing.
Exactly. As the temperature climbs past that 0 degrees Celsius mark, that rigid crystalline structure just dissolves. It breaks down. You can see it happening.
So this sounds like Aqua is getting a bit more freedom now.
Well, now you have a flowing mass of H2O molecules. They're shimmering, sliding past each other. Aqua is moving around, bumping into neighbors gently, tumbling over them.
There's a lot more movement than before.
Oh, significantly more freedom.
Yeah.
And that's why liquid water takes the shape of its container, right? It flows. Pour it from a beaker into a dish, it spreads out.
But its volume stays the same, doesn't it?
Visibly consistent, yes. Unlike a gas. That's because even with this newfound freedom, there are still forces holding them loosely together.
So the intermolecular forces aren't gone completely, just different.
Precisely. They're weaker now, more flexible.
Okay, so for liquid water, medium kinetic energy.
Right, more than ice.
And weak intermolecular forces. Connected, but loosely.
That sums it up well.
Now, something interesting happens even before boiling. Evaporation. What's going on there? Why do some molecules just leave?
Yeah, that's a neat one. Even in a liquid, not all molecules have the exact same energy. Some, just by chance, especially near the surface, might get an extra burst of speed.
Like a random energetic kick.
Kind of. Enough energy to overcome those weak intermolecular forces holding them in the liquid. And poof, they leap out. Some float away into the air. Others might lose energy quickly and fall back into the liquid.
I see. And then as we keep adding heat, we get closer to boiling. We start seeing those little bubbles, right?
We do. It's anticipating the big change.
The big change being the gaseous galaxy, total freedom, the final state.
This is where things get really energetic. The liquid becomes intensely agitated. Think of a pot at a rolling boil.
Yeah.
It's just swamped with high-energy heat particles. The molecules are bouncing off each other with incredible force and speed.
What does that look like visually when it hits that point?
Well, instead of just small bubbles from the bottom, you get large, vigorous bubbles forming within the bulk of the liquid. They rise up really fast, burst at the surface,
Releasing the gas.
releasing streams of vaporized molecules. Steam, this is Aqua's total liberation moment. She gets propelled upwards with this huge surge of kinetic energy,
Whoosh.
breaks free from the liquid surface entirely, and just shoots off rapidly into the surrounding space.
A space our source called a gaseous galaxy. So thinking about this, what should you, our listener, take away? Maybe the next time you see ice cubes in a drink.
Pause for a second.
Yeah, pause and think about what's really going on at that unseen level. It's all physics. Fascinating stuff.